This is just a quick video to cover the concept of dead states in finite state machines. You should have watched the previous two videos on deterministic finite state machines and you should know how they operate. Let's imagine we want to design a machine for the simple language that consists of only the strings 101 and 110, with the alphabet just the symbols 0 and 1. We could do that with this simple finite state machine here. It looks fairly elegant. We process the first string along the horizontal path and the second string by taking the bottom path. No loops or anything confusing. The only problem is according to the definition of the deterministic finite state machine we already have, this isn't valid. Each of the states needs a transition out of it for every possible symbol that could be encountered. The only state that's actually valid according to this is Q1. All of the others, including the accepting state Q4, are missing at least one transition out of them for a particular symbol. To see why this is a problem, imagine that the machine was given a string starting with the symbol 0. Now, by our definition, a finite state machine has to halt once it processes all of the input string and then either rejects if it is not in an accepting state or accepts if it is in an accepting state. The problem is this diagram that we have here, if we reach Q0, has nowhere to go upon seeing a symbol 0. Therefore, it can never consume all of the input and then halt. So, let's fix this problem. We'll add an extra state, which we'll call the dead state, and we'll transition into this state whenever we know for certain that the string that we're dealing with cannot be in the language. So for instance, if we saw a string starting with the symbol 0, while we're in state Q0, we could transition into this state. Now the problem is we could see any number of zeros and ones after this, because a string can be made up of any combination of these symbols from the alphabet, and the machine has to deal with any such of those strings. So what we do is we add a loop back onto that dead state that transitions on every element of the alphabet, in this case 0 and 1. So if we saw the string 0, 1, 1, 1, we would transition into the dead state, then we would loop, consuming all of the ones, and by the time we'd consumed all of the symbols from the string, we'd be sitting in a non-accepting state and the machine would halt and reject. So let's add this condition for every of the possible states that we have in this finite state machine so that we can have an actual valid finite state machine. So from Q2, if we saw a 0 at this point, we would immediately not have something in the language, so we would have to transition into the dead state. Same for Q3 if we saw a 1. And also, when we've finished, if we see a 101 or a 110, but then we have a longer string with more zeros and ones, we'd have to transition out of the accepting state and into the dead state. Now the problem with this is you can see that this is far less elegant a design than the original finite state machine we had. Clearly, it would be preferable to have a nice elegant design like the one here. So, what we will work with is the assumption that if the machine is in any state and there is not an explicit transition out of that state for a particular symbol, the machine is assumed to transition into the dead state. So all of those extra transitions that we drew on before would just be assumed in this case. So we can see that the machine is still elegant, contains all of the information that we need, and using this assumption is still correct. So to clarify, a dead state, D in this case, is any state from which it is impossible to reach an accepting state. So in this we can see that the reason it is impossible is because all of the transitions out of D lead straight back into D, and D itself is not accepting. Q4 would not be a dead state if it had a loop like the one here, because it itself is accepting. And the assumption made is that whenever we have a transition not explicitly on the diagram, we assume that it transitions into the dead state. So be careful to make sure you don't leave anything out on your diagrams. The only thing you need to know from this video is what a dead state is and what assumptions we make when we do not have transitions explicitly labelled on our finite state machine diagrams.